Hello everyone, welcome to new class. Next is magnetization curve or BH curve. BH curve is the graph between flux density B and the magnetizing force H of a magnetic material. And the following figure is BH curve for cast iron. So this is BH curve. Initially the magnetization force H increases rapidly with B, that is with flux density B, up to a certain point. The rate of increase of flux density becomes very low and finally reaches steady state value, that is saturation of the material takes place. Now let us study about magnetic hysteresis. So this is very important portion in the magnetism, magnetic hysteresis. And it is the lagging of flux density behind the magnetic force in a magnetic material. Let a magnetizing force H be applied to an unmagnified bar of iron. Let the magnetizing force H be increased from 0 to a certain maximum value and then gradually reduced to 0 again. The curve OAB is obtained. At the point B, the magnetizing force H becomes 0. But there is still some magnetization left in the material. That is, the flux density B does not fall to 0. The remaining value of B at the point is called residual magnetism. The power of retaining the magnetism is called retentivity of the material. Also, the flux density represented by OB is called remanence. Now, in order to demagnetize the iron, the value of H is reversed. B reduces and becomes 0 at the point C. The value of H required to wipe off residual magnetism is known as coercive force. That is, coercive force is the value of magnetizing force. Here it is represented by OC. Further increase of H in the negative direction, curve CD is obtained. Now the gradual decrease of H to 0 and then a build-up in the original direction is described by the curve DEFA. As H is increased and then decreased to its original values, the flux density B does not return to its original value. This fact is called hysteresis. And the curve ABCDEFA is called the hysteresis loop. That is, the tendency of a magnetic material tending to retain a portion of its magnetic properties is known as hysteresis. Magnetic circuit. A magnetic circuit is a closed path followed by magnetic lines of force. And this magnetic circuit is of two types, series and parallel. That is composite magnetic circuit and parallel magnetic circuit. Composite magnetic circuit. or we can say reluctances in series. In several cases, the magnetic circuit consists of several regions of different materials and different dimensions. The figure shows four regions A, B, C, D of length L1, L2, L3 and Lg. Lg is for this air gap respectively, and the area of cross sections are A1, A2, A3 and Ag. Each of these regions has different reluctance. Then the total reluctance of the circuit is sum of individual reluctances. That is total reluctance S is equal to S1 plus S2 plus S3 plus S4, and we know reluctance S is equal to L by mu into A. That is L1 by mu1 A1 plus L2 by mu2 A2 plus L3 by mu3 A3 plus Lg by mu0 Ag. Here mu0 is because it is air gap. So we can write mu0, that is mu is equal to mu0 into mu r, and for air the relative permeability is 1. So we get mu0. Next is parallel magnetic circuit, or we can say reluctances in parallel. A magnetic circuit which has two or more than two paths for the magnetic flux is called parallel magnetic circuit. The figure shows a magnetic circuit excited by a current of I ampere passing through n turns of the coil placed in the central limb, and the MMF creates a flux of 5 Weber in the central limb, and this flux is divided into two fluxes phi 1 and phi 2 in the outer limbs of these length L1 and L2 respectively. And we have here this flux is divided into 2, so the total flux phi equal to phi 1 plus phi 2. And in this case the total reluctance S is equal to S plus S1 parallel to S2, that is S is the reluctance of the central limb and S1 and S2 are the reluctances of the parallel limbs. So the total reluctance in this case is S plus S1 S2 divided by S1 plus S2, or in other way we can say 1 by S equivalent is equal to 1 by S1 plus 1 by S2 plus 1 by S3. That is, for the parallel magnetic path, the reluctance is, the total reluctance is 1 by S is equal to 1 by S1 plus 1 by S2 plus etc. And here the MMF in the parallel path is same. So the total MMF required is in this case phi s plus phi 1 s1, that is the MMF of the central limb plus MMF of this path, or MMF of the central limb plus MMF of this path, that is phi s plus phi 1 s1 or phi s plus phi 2 s2 is the total MMF required in this case. Now let us go through a problem. An iron ring having cross-sectional area of 400 mm square and mean circumference of 500 mm carries a coil of 250 turns wound uniformly around it. Calculate reluctance of the ring, current required to produce a flux of 1000 microweber in the ring, relative permeability of iron is given by 400. And here we have given cross-sectional area 400 millimeter square, that is 400 into 10 raised to minus 6 meter square. And mean circumference is nothing but the length is 500 millimeter, that is 500 into 10 raised to minus 3 meter. Also the number of turns is given and the relative permeability mu r is given as 400. The first question is to find the reluctance of the ring, and we know the reluctance S is equal to L by mu 0 mu r into A. Here all the data are given. L is 500 into 10 raised to minus 3 and mu 0 we know 4 pi into 10 raised to minus 7 Henry per meter, and here mu r of iron is given as 400. Area is 400 into 10 raised to minus 6, and by solving this we get 2488 into 10 raised to 3 ampere turns per Weber as the reluctance. And next we have to find the current required to produce a flux of 1000 microweber in the ring. For that we know mmf is equal to flux into reluctance, and mmf is given by N into I. N is the number of turns and I is the current, that is equal to phi into S. And here from this current I is equal to phi into S divided by N. Phi is given as 1000 microweber, that is 1000 into 10 raised to minus 6 into reluctance now we get, and number of turns as 250. After solving this we get 9.952 into 10 raised to minus 6 ampere or 9.952 microampere. Next question. A mild steel ring has a mean circumference of 500 millimeter and a uniform cross-sectional area of 300 millimeter square. Calculate the mmf required to produce a flux of 500 microweber. Assume mu r equal to 1200. So how will you do the problem? First of all, write down the given data in SI unit, that is length is given in millimeter, so convert into meter, also area, and also flux is given in microweber, so convert into Weber, and mu r, that is relative permeability, is given by 1200. The question is to find the mmf required. We know mmf is N into I, but here the number of turns is not given and also current is not given. We know another equation relating mmf, that is mmf is equal to flux into reluctance. So first we have to find reluctance, and we know reluctance S is equal to L by mu 0 mu r A. L is given 500 into 10 raised to minus 3. Mu 0 is 4 pi into 10 raised to minus 7. Mu r 1200, and area of cross section is 300 into 10 raised to minus 6. After solving this we get 11,05,803 ampere turns per Weber, or we can write 1.1058 into 10 raised to 6 ampere turns per Weber. Now we can find mmf using the equation mmf equal to phi into S. Phi is given as 500 into 10 raised to minus 6 into the reluctance value, and we get 552.9 ampere turns. The unit of mmf is ampere turns. Next question. An iron ring of mean length 60 cm has an air gap of 2 mm and a winding of 300 turns. If the relative permeability of iron used in the ring is 400, when a current of 1.5 ampere flows through it, find the flux density. This is a problem of composite magnetic circuit, that is series reluctance circuit. We have to find flux density B. So let B be the flux density in Weber per meter square. We know H is equal to the magnetizing force, H is equal to Ni divided by L. And we have B equal to mu into H. Then from this mmf is N into I, that is equal to H into L. And substitute the value of H in terms of B, we get B by mu into L. Now write down the given datas. Here first find the mmf required for the iron ring. Let L1 be the length of the iron ring and L2 be the length of air gap. And these two are in series. So first find mmf for the iron ring. Let mmf 1 be the mmf required for the iron ring, then that is given by, that is substitute in this equation, we get B into L1 divided by mu 0 into 400, that is mu is equal to mu 0 into mu r, and mu r of iron is given as 400. Then next is mmf required for the air gap, that is mmf 2 equal to B into L2 divided by mu 0 into mu r is 1 for air gap. Now substitute the values. B into L1 is given by 60 into 10 raised to minus 2 divided by mu 0 is, let mu 0 be written as mu 0 into 400. Then here B into L2 is given 2 into 10 raised to minus 3 divided by mu 0 into 1, that is mu 0. Now for a composite circuit, total mmf is given by mmf 1 plus mmf 2, and we get, adding these two, B into 60 into 10 raised to minus 2 divided by mu 0 into 400 plus B into 2 into 10 raised to minus 3 divided by mu 0. Taking B and mu 0 outside, we get B by mu 0 into 60 into 10 raised to minus 2 divided by 400 plus 2 into 10 raised to minus 3. And substituting the value of mu 0, that is 4 pi into 10 raised to minus 7, here we get B into 2786. And we are given the current flowing. So the mmf provided by the current is given as N into I, that is N is given 300 into current is 1.5. Now equate these two, that is B into 2800 2786 equal to 300 into 1.5. From this we get the flux density B equal to 300 into 1.5 divided by 2786, that is equal to 0.1615 Weber per meter square. These type of problems are very important. Thank you for watching the video. If you like the classes, please like, share with your friends and also subscribe my channel.